Hi, everybody. My name is Chenguang Zhu. I'm from Microsoft. Today, I'm going to talk about boosting naturalness of language in task-oriented dialogues via adversarial training. Natural language generation, or NLG, is an important and final part of a task-oriented dialogue system. It directly faces customers, so its quality directly impacts the user's impression of the system. Current NLG system usually uses traditional sequence-to-sequence framework. However, the generated sequence usually lacks the variation and fluency of humans. For example, here, the meaning representations of slot values talk about a restaurant called Wildwood. As you can see from the red color, the generated information with the sequence-to-sequence system puts the two location information in different sentences, which is against humans' language patterns. So to alleviate this problem, several methods can be used. First is reinforcement learning. However, RL needs to get signals from non-differentiable quality scores, such as blue, if we do not want to have a human to be with the training all the time. But is blue itself a good indicator? This is questionable. Another way, which we use in this paper, is adversarial training. In this framework, we use a pair of generator G and discriminator D. D is a classifier that tries to tell apart human utterances from G's utterances. Okay, let's look at the formal formulation of the problem. Given meaning representations or MR in terms of slot and values, and also the dialogue acts or DA, such as inform and request, the system needs to generate response in a natural language. We adopt the sequence-to-sequence framework as the baseline. Both encoder and decoder use RNN. And we use attention mechanism in the decoder to attend to encoder outputs. And the system is optimized using the cross-entropy loss function. Then we employ the GAN, or generative adversarial network, to introduce the naturalness training. Here, the generator D and discriminator D play a game together. While G tries to fool D by generating utterances like human, D tries to tell the difference between real utterances and G. So D itself is a classifier that projects an utterance to a score between 0 and 1. Based on this loss function, we can see that when the sentence comes from the real ground truth, D wants to maximize the score. Otherwise, it wants to minimize the score. And G tries to do exactly the reverse thing. But directly optimizing this loss function has a problem because the text generated by G is composed of discrete tokens, so the gradients cannot pass. One way is to use RL again, but it involves sampling from a lot of utterances generated by G, and it can suffer from high variance. Therefore, we use a straight-through Gumbel Softmax estimator, which looks like this. Here, the PTI is the predicted logit for the ith word in the vocabulary in the tth step. So Gumbel Softmax basically adds a Gumbel variable GI to the logits, and then use the softmax to get PTI prime. So this can be sent to the downstream for computation, and the gradients can be computed directly. And here, I want to introduce a coding trick for Gumbel Softmax. Here, the example is in PyTorch. The y hard is the argmax of the one hot vector, which points to the token that the generator generates. While y is the result of Gumbel Softmax applied on the predicted logits. Using this line, it can ensure that in a forward pass, only y hard is used because it's y hard minus 1 and plus 1. But in backward pass, y hard is thrown away, which is non-differentiable. Only y takes the gradient, since detach removes the component from the gradient graph. Here is the full architecture of our proposed model, AdvNLG. As you can see, the generator is based on sequence to sequence, and it is optimized by cross entropy. The discriminator receives both the input from the generated stuff from the generator, y prime, and also the real utterance y. In experiments, we found that at initial stage, the generator G produces utterances of really bad quality. What this induces is that the discriminator D tends to overfit because the task is so easy. Therefore, the training cannot proceed as expected. So we warm up the training of G using the cross entropy for a few epochs before co-training G and D. This two-stage training proves to be very useful. We conduct experiments on E2E, NLG, and RNLG datasets. As you can see, our model outperforms previous baselines in both automatic metrics and human evaluation. And we did ablation studies using RL instead of Gumbel Softmax, and also removing the adversarial part, also removing the two-stage training. All of these ablated versions show that our proposed component are useful. Last, I want to show an example of the generated utterances. So here is this media representation is talking about some reviews, information about the restaurant. As you can see, in one of the baselines, it puts a relatively negative comment, customer rating low, and a positive review like child-friendly together, which is against human usage. But our model puts the relatively negative comments together and put the positive comments in a separate sentence, which sounds more natural. Okay, thank you very much for listening.